Okay, so I guess everyone's pretty much done the lab, hopefully. So we, again, I think those you can turn into the TA who is Thiago, and he said he would be available on Mondays and Wednesdays from 1 to 2 p.m. And I believe on the in the 8th floor on that in that little area there, that congregating area outside of the conference room. So is that okay with everyone? He was 3:30 to 4:30. But I guess he had some issues with his group meetings coinciding with that time, so he asked if he could move it over. So, and I'll be available like after class, and you can, if you have other questions, you can shoot me an email or something, and I'll be happy to respond to those. Let's see, there.
Isn't there one more lab section tomorrow?
No, we had 3. We had Monday morning, afternoon, and this morning.
Missed it.
Oh, you missed it?
But mine is Wednesday.
Oh. Why don't you talk to Silvana and see what you can do to schedule something. Yeah, so the lab sessions, again, so we don't overburden my students too much. Again, they're Monday in the AM from 9 to 11, and in the PM from 2 to 4, and then Tuesday from 10 to 12. So those are the lab sessions. And again, so I think you could turn your assignment, your lab write-ups into Thiago. If he has a problem, he'll maybe give them to Silvana or to me or whatever, so we can get those worked out. Were there any comments on the lab?
Is there an office or something we should drop them off on if we have them?
Well, I could take them if you have them here, but let's see, and if you're over in ECE, you can drop them off in my lab. Usually just knock on the door, and you can put them on a refrigerator. That seems to be the common place, like in any home. So anyway, if you do that, we'll take care of it. So were there any other questions on the lab? I think it went pretty smooth. I'm glad Silvana allowed you to kind of stumble through some of the alignment. I think that's very helpful to kind of learn how to do that sort of thing on your own. So that lab is pretty easy as far as the holography goes. So there's a little bit of extra time there to kind of to work on things, to get a little hands-on in the process. So also, if you go on the D2L site, I put up homework number 2. This one, homework 2, comes out of Goodman's book. A couple of problems from Goodman's book. They're a little bit more involved. So maybe if you, what I'd like you to do is to I believe it's from chapter 4, but I basically copied them out of his book and put them up. So they're a little bit more involved, and so next time I'll make some comments on those so you can have an idea of better how to solve them. I think after today you'll have a pretty good idea how to approach them, and but after Thursday I think you'll be able to get started on those. So anyway, so that's in store, and then there'll be another lab. I will look at the scheduling and get that set up shortly as well. Okay, so last time we saw that we developed a couple of powerful techniques for analyzing diffracted fields, and so we have both the Fresnel diffraction formula, okay, and both of these really depend upon the propagation distance. So this one kind of revolved around the approximation of taking that radical that we had for RO1 and making, so we had that radical distance or radical describing the propagation distance between our aperture and observation point, which was, I guess we had a z out front here, times the square root of 1 plus x minus psi over z squared plus y minus eta over z squared. And this was in the form of a binomial. This square root was in the form of a binomial. And so for the Fresnel approximation, we took just the first two terms of that, which were 1 plus 1/2 b, where b is basically equal to this value. We said z was much greater than the various distances in the aperture, and so that put us in a particular domain of diffraction. And with that, we ended up with the diffracted field. So on our observation plane, or observation region, we have a bunch of sort of constants outside of an integral, which were phase terms. So we have e to the j kz. We also have a scaling term, j lambda z, and then exponential of j k over 2z, x squared plus y squared. So we have this quadratic outside the integral. But then the most important term is this integral relation that we have, which is basically the Fourier transform of the field in the aperture. All right, so we have u of chi eta times a quadratic phase factor. This is the sort of the characteristic of the Fresnel region, is this quadratic phase factor, jk over 2z chi squared plus eta squared. So that is being, this term here is being Fourier transformed, and the Fourier transform kernel is this exponential e to the minus j 2 pi over lambda z x chi plus y eta integrated over the aperture d chi d eta. All right, so here's the observation plane. This is in the aperture plane. And so we end up with this relationship. So this stuff is, you know, kind of, it's a function of x and y, but these are functions in the observation plane. Outside of the integral, all of these are where things are happening. And we saw that one of the characteristics of this Fresnel diffraction region is that the functional form for that diffraction pattern changes with distance. So again, so this is very important and characteristic. So if we're at one distance, we may have, you know, maybe a function that looks like a diffraction pattern that looks like that over this aperture with a peak in the middle. And as we move, say, a distance, another distance z away, here we have something that may have a maybe a null in the middle instead. So the functional form for that pattern is varying as we move further away from the aperture, and the aperture may be out, say, out here somewhere. So this is our chi and eta direction that we have there. Okay, so that's our Fresnel diffraction, and then we are looking at this and saying, okay, so how can we, so if we continue to propagate at farther distances away, you know, what does that diffraction pattern look like? And so there we notice that, you know, we can actually come to a distance where this quadratic phase term goes to 1. And so in that instance, we would just have the Fourier transform of the aperture function itself. All right, and so that is again the far, what's called the far field, or the Fraunhofer region, and it's a region in which the distance is far. Oh, let's. It's a region in which the distance, again, is pretty far away from this this aperture out here. All right, so this is k over, and again, k is 2 pi over lambda, so that's a pretty big scaling factor times the maximum, say, value for this aperture that we have. So, and these are kind of the max values out here, and actually that's much greater, not just greater than. And so in this case we have that the field, the diffraction pattern in the observation plane u of xy is equal to e to the jkz e to the jk over 2z x squared plus y squared over j lambda z again, so that same factor basically out front. But now we've eliminated that quadratic phase factor, and so we end up with just u of chi and eta, exponential of minus j 2 pi over lambda z times x chi plus y eta, and that is integrated over d chi d eta. All right, but again, this distance is considerable, and then shortly, either this time or next time, we'll see how we can eliminate that. But if we had, for instance, if we had an aperture, say the eta max was on the order of an inch, say 2.5 centimeters. We have a wavelength, maybe 600 nanometers. We find that z's got to be pretty far, much greater than about 1.5 kilometers. Okay, in that particular case. So that's a big aperture, but still, not an unusual one that we might experience. Yes.
Is that a negative I in the exponent inside of the integral? Or
Over here?
yes.
Yes, that's a negative j. Yeah, as well. Let's see. Yeah, so here the kernel, the exponent is a negative. This one's a positive here, but the integration kernel for that Fourier transform is a negative, which again, that's consistent with our definition that we talked about a while ago, where this was our definition for the Fourier transform. Okay, all right. Okay, so with that, we wanted to look at a couple of different apertures, and so we looked at the rectangular aperture. So again, the process here is that we looked at an aperture here, and this has here's chi and eta. This is wx and wy. Distances like that. So this then gives us a transmittance function, which is again our aperture function. So we have an amplitude transmittance function, chi and eta, which is rect of chi over 2 wx and rect of eta over 2 wy. And if we illuminate this with this normally incident plane wave, we then form a field, right? So now we have u essentially of chi and eta is equal to t sub a of chi and eta. And with that, we saw that the Fourier transform of the rect is the sinc function. These, notice too, these are independent variables in the orthogonal directions. As in optics, we're talking about two-dimensional transforms. So we end up with sinc functions, and if we wanted the intensity, which in general is what we want, we would square those sinc functions, so we end up with a I of, or an intensity, again, of xy is going to be, works out to be the area squared over lambda z squared, sinc squared of 2wx over lambda z. So x over lambda z, that's our fx, right? Fx is x over lambda z, and we also have a sinc squared in the y, which is 2w, I guess this wxx and wyy. They could be different over lambda z as well. And similarly, we'll have f sub y is equal to y over, lambda z or z lambda for the spatial frequencies, since we're talking about Fourier transforms. That is the form for that diffraction pattern that we have. And again, so I mean, these are simple patterns, but the thing is, these patterns, we're going to work on these next and use these in a couple of little more, well, in some more, a little bit more complexity into the aperture function. But these are nice, you know, overall envelope type functions that we'll be seeing time and time again. So this, of course, this sinc squared function is an oscillatory function, like so. And it has minima here at 1, integers 1 and 2 and so forth, where this is, say, the abscissa here is 2wx x over lambda z. So again, this also shows the this scaling rule that we had. The area is 2wx times 2wy for that system. So that, again, comes out from the, where we invert that factor times the variable, and it also comes outside of the function. Okay, so that was the rect function. We also had that circ function. Again, so in optics, again, all lenses, well, not all, but you know, I'd say 95% of the lenses are circular, and so you're always going to have an envelope function that looks like this diffraction pattern from a circular aperture, provided your aberrations are not that large. So a diffraction limited spot is, again, this is where the diffraction limit comes from. It comes from these diffraction patterns from these various aperture functions. So here for the circular function, here we have, again, we may have some maximum radius of w and a variable q out to some distance, where this is in, again, the aperture plane. Q is equal to square root of chi and eta squared. And we can write the transmittance function in this case as t sub a of q is equal to this circ function now of q over w. So the circ function is basically a hole, a circular hole. So if we, again, illuminate this with a normally incident plane wave, we'll then get a field u of q now, which is equal to t sub a of q. All right. So we have the same process occurring if we want the far field pattern basically what we're going to do is we're going to take the Fourier transform of that u of q, and then we have to multiply it by these other phase functions and a little bit of scaling in order to get the diffraction pattern in the far field. But in this case, the Fourier transform for this circular function is perhaps best represented by a Fourier Bessel function. And so this now we would, instead of this Fourier transform in Cartesian coordinates, we would perhaps write this as a Fourier Bessel function of u of q. They're equivalent. We could go in Cartesian coordinates, but again, it's easier to use this form. And the transform variable, whereas we have q in the spatial domain, we will have now rho in the frequency domain, which is the square root of fx squared plus fy squared, which again is the radius in the spatial frequency domain or in the diffraction plane region. All right. So now the nice thing about this Fourier-Bessel function is we know these functions. We can look them up, and so this Fourier-Bessel function of the circ of q over w, as we mentioned, is the area times this j1 function of 2 pi over w rho divided by pi w rho. Okay. So it's kind of interesting. This function has kind of the same functional dependence as the J0 function, but it's derived differently from an analysis of the diffraction propagation. Okay, I actually looked this up today just out of curiosity because I was playing around with some Bessel functions and had the fact that the J0 function has actually the same functional form as this J1x over x, or J1 of 2x over 2x. So again, in kind of putting this all together, the intensity pattern in this case out in the diffraction plane, the far field diffraction plane, now it works out to a over lambda z squared again, times this very characteristic function, this 2j1 of k, or 2 pi over lambda wr over 2 over k wr over 2 squared. All right, so all right, and so this r is just, this is the spatial frequency, and so the r is actually the spatial coordinate in that far field pattern. Okay, just so if you're curious about that. Notice r is multiplied by k, which is 2 pi over lambda, so we end up with kind of I'm sorry, there should be that is z, not 2. I was wondering, yeah, it has to be, that's the spatial frequency, right? So we have r over lambda z as the spatial frequency, or we can write it in terms of the coordinates, which again is a little easier to depict. And again, if we plot this, we have something that looks similar to that sinh squared function, but the zeros are not equally spaced. So this one is the first one's at 1.22, the next zero here is at 1.635, and so forth. And this is 2wr over lambda z, writing that in terms of the actual values of lambda z rather than the frequency or the k value. And the width between these, again, we kind of talked about this a little bit in that spectrometer problem, has a value of 2.44 lambda z over 2w, where again w is the width of that circle, and the delta r, the radius of that center spot, is we can write that as 2.44 lambda z over d. Okay, so and d is 2w, twice the radius. All right, so we see this is looking a little bit like the f number. So if we had a lens which focused that, so this we might consider also the f number of our lens if that was a lensing system. But if we just had the aperture, say like for a pinhole camera or something like that, you could still get the same sort of focusing effect from that pinhole. Okay, so again, I spent a little time going over those just, some students are not coming directly from an optics background. And also, I just wanted to emphasize the fact that these kind of basic aperture functions, the rectangle and circle, appear over and over and over again. And so it's not a bad thing to just kind of quickly go through that. Okay, so now let's do something a little different. I want to look at a problem that you've probably encountered somewhere in your physics or optics classes in the past, and that is the Young slit experiment. However, this time we're going to approach it using these Fourier tools that we just went over. So again, I actually borrowed this out of Goodman's book. It's one of the problems in there. So I'll solve this problem for you rather than assigning it. Yeah, I know. His problems are a bit more challenging, but very insightful, I think. So I know I had a lot of good time solving those problems when I was his student, taking his classes. So okay, so here we have a kind of a Young slit problem, and you can solve this problem doing kind of ray matching, ray analysis through the slits and going out to some distance, and you end up like with an interference pattern, right? You're going to get some kind of interference pattern from light that's propagating through these two slits. These are, again, rectangular apertures, so they have, say, a width in the along this chi direction here of capital X, and they have a width in the eta direction of capital Y. And the other thing is that we have two of them. All right, so we have a separation distance we'll call delta between these two. All right. What?
Between the centers?
Yeah, between the centers. Okay. Yeah. All right. So, it's kind of like a grating, right, with only two cycles, or one cycle, however you want to count it. All right. Okay. So, again, we can follow our same simple rule for doing this analysis. What we want is, again, the far field pattern and so what we want to have is a transmittance function for this aperture, right? This is just an aperture. So here this is blocked, and all around here, and this is clear. Okay, so the amplitude transmittance function for this double slit we can write in the following way. We have that t of chi and eta is equal to a rect function in the x direction, right? So we have rect of chi over x, capital X here, in that direction. Notice there's no oscillation or no repetition in that direction. But we do have these two cycles in the eta direction, all right? So here we have rect of eta minus delta over 2 over y. Oops. All right, and we also have plus rect of eta plus delta over 2 over y. Okay, so again, just a simple way of expressing that. However, let's kind of play around with this a little bit now that we have some Fourier analysis tools, and we know that we're going to be looking after taking a Fourier transform of all this. So if we look at this function that we have here, this one's more, we know that this is just going to give us a sinc function of some sort. So that's pretty much solved. So the action is going to be here in this this eta direction, or the y direction. All right. Okay. So if we look at that function that we have here, this can be written as being equal to the rect of eta over y, right, convolved with what? It's going to be convolved with two delta functions that are displaced by minus delta over 2 and plus delta over 2. And so we can write that as a convolution of eta minus delta over 2 plus delta times eta plus delta over 2. All right? So why are we doing that? Well, remember, we're going to be taking the Fourier transform of this function. And we have a convolution. So the Fourier transform of a convolution in one domain is going to be the product of the functions in the other domain. Okay. Now, the nice thing about the delta functions is, as we just noticed here, it represents a sort of relocation of the center of this function that we're convolving it with at the centers of these, or where these delta functions are located. Okay. So if we were then to, and something else now. So what we're going to want to do is take the Fourier transform of this and take the Fourier transform of these, and then multiply them. Okay. So again, we know the Fourier transform of that's going to be a sinc function, but the Fourier transform of this delta function, so we have Fourier transform of delta of eta minus delta over 2. That is equal to what? That is going to be equal to, remember from our relations, well, we have a displacement gives us a shift. Remember our shift theorem that we had? So this is just, and a delta function is just the constant, but we're going to end up, when we have this displacement, we're going to have this phase term in the from this shift that we have here. And so this is just going to be equal to e to the minus j delta over 2 times our spatial frequency in the y direction, which f sub y is equal to y over lambda z. And then just for completeness, f sub x is equal to x over lambda z. Okay, so, and again, so this term here is due to the fact that we have this shift, and the Fourier transform of a delta function is just equal to 1, right? So we end up with a magnitude of 1 out in front, okay? So delta functions are our friends. You know, they can really simplify the problem a great deal if we see how they fold out of a particular function that we need to manipulate. All right, so we have a minus there. We also are going to have a plus. So we have a plus, or a plus e to the j delta over 2fy, and a plus a e to the minus j to delta over 2fy. So that's going to look like what? Cosine function. Yeah, so we can say then that this that we have out here, the Fourier transform of that, is going to be equal to 2 cosine of pi delta fy. And that's equal to, again, e to the minus j delta over 2 times 2 pi fy plus e to the plus j delta over 2 pi fy. All right, that's where that comes out. So these 2's, again, cancel. Here, here, here. We need this over 2, so we have to multiply by 2, so that's where we get that 2 from. And so that's what we have from the Fourier transform of this second term here. So that is basically going to be multiplied by this the transform of this function. So we have this function times the transform of that function. And then we also have this one up here, which also gives us some sinc functions. So in the end, we're going to have a field function u of xy in the far field, which is equal to, say, a phase constant, or phase constant, with all that other stuff that we have normally out in front of the Fourier transform, times 2 xy from scaling, because all these have magnitudes of y and x, so that has to come out. And then we have from this function, we have a sinc of x over lambda z. And then we have the this Fourier transform from that is again a sinc of y, cap y, y over lambda z, and then we have a cosine. So that 2 comes from here. So then we have a cosine of pi delta fy. All right. And and again, the intensity again is we have to take this times its complex conjugate. So we end up with 4 xy, which is like the area over of these rectangles that we have, over lambda z quantity squared, sinc squared of x over lambda z, sinc squared of y over lambda z, sinc squared of, cosine squared of delta y over lambda z. Okay, so that's the function that we have, and so what does it look like? Well, if we take some values of this x over lambda z, we'll let that equal to, this has dimensions of inverse meters, so we'll take just 1 meter inverse y, cap y over lambda z. That will also have as 1 meter inverse, and we'll have delta over lambda z. That will take as 1.5 meter inverse.
That's a question. I guess, how did you find that C utility value there?
Oh, that's just equal to this stuff. I just didn't want to write all that. Okay. And that this lambda z came out of the fact that we have this lambda z in that denominator. Everything else is a phase term, so that'll kind of go away when we do the intensity. Okay. Sure. So I plotted this out. I was playing around with this again and plotted this out just for fun here. So here in the x direction, again, you just get this sinc function. Notice it goes to 0 at the 1 here. But in the y direction, again, so we get this kind of oscillation, which is kind of changing. Again, it has a sinc squared times a cosine squared envelope function. All right. So basically, we have a cosine, which would again give us nice uniform amplitude. This would come back up again, but it's sort of modified or weighted by the sinc squared function, just like it is here. So again, that drops off. Notice here this other lobe is reduced, out at that point. So again, it's a way of solving some problems that you normally solve by, say, ray tracing and phase matching and so forth in a much more straightforward way. We can use all these convolution aspects and Fourier transform giving us the products, and hopefully, by shifting some of these terms around too, like displacing these with delta functions, we can use the properties of the delta function to also further simplify things. So whenever you're solving a problem like this, it's always useful to kind of put it in context of some of these very powerful relations that we now have. So again, that's one of the interesting things I think about Goodman's book. Again, I highly recommend that book because he has a lot of examples in there of how to use the Fourier transform to really good advantage in analyzing optical systems. So let's take this a couple of steps further. So now that we have these tools, let's look at some things that are really relevant to the class. Let's look at some gratings. Okay, so we can basically we can model the grating as just a special transmittance function. All right, so we're going to look at the grating as a transmittance function. And then we'll use the Fourier analysis to determine the kind of the diffraction pattern. And in addition, in certain cases, okay, and the cases are for thin gratings. You know, we define a thin grating as basically being one scattering plane for the diffraction process to occur, so we don't get this selectivity buildup that we would from interacting with multiple planes, but we just have this one set of scattering points which gives us the diffracted field. We can actually also determine the diffraction efficiency. And the diffraction efficiency for these thin gratings is in a certain type of grating strength regime, and which was first identified by Raman and Nath. And so sometimes this is called the Raman-Nath regime for diffraction efficiency of gratings. Okay, so later we're going to spend a fair amount of time talking about coupled wave analysis in the class, and that will give us the kind of the thick or volume grating regime where we'd be operating, and there we can get much higher efficiencies than we'll see here for the for these thin gratings. But nonetheless, both are important, and in general, we went to a kind of a rigorous analysis where we solved the full electromagnetic kind of model for grating diffraction. We don't have to specify which regime we're in, but the grating parameters themselves will determine what the efficiency is for the grating. Okay, so let's go ahead and look at this. All right. So first, let's look at a thin absorption grating. All right, and so for this, we're going to have our amplitude transmittance is going to look something like this. So here we have T sub A, and so we're going to have a modulation that looks something like that. This might be, say, at 0.5. So again, remember we talked about this HD curve here, and we have an exposure and we have a density. So we're going to be looking at somewhere in this linear region. So this might be, say, at this 0.5 amplitude transmittance that we have here, and so we're going to be modulating about that point. And so this peak-to-peak value that we have here, we'll say has a modulation value of m. Like so. And we have a period out here we can call lambda, or we also can say that this has a spatial frequency. So in that last homework set, I was asking for spatial frequency. What I was, some of was kind of after just looking at the inverse of the period for that. So we have a period here of a lambda, and this is, say, going to be in the chi direction, like so. All right. And so again, so this doesn't extend for infinity, right? So we're going to have a grating that's going to look something like this. So there's an aperture, and we'll put a rectangular aperture on that. All right, and so here, so again, so what we'll have is this, we have this amplitude modulation with the period here of lambda. This is, say, chi, and this is our eta direction. And so we'll have a half width here of W. And so with that, we can write the amplitude transmittance that we have, T sub A of chi and eta. This is equal to the modulation term, which is, say, 1/2, which is this term that we have here, plus the modulation, m over 2. So that, is the half, the peak above that bias level, m over 2, cosine of 2 pi times this frequency f0 times chi. All right. So we have that, and then we also have the kind of the overall envelope function, or in this case, it's a rect function in both directions. So we have a rect function, and we'll make it square. So it's just rect of chi over 2w and times rect of eta over 2w. Okay, so again, that is our amplitude transmittance function. And again, just as we've been doing all along, we can convert that into a field, all right, of chi and eta. If we illuminate this, again, with a normally incident plane wave, unit amplitude normally incident plane wave, and then we have that the field just past the aperture here, which is going to propagate in our z direction, is this u of chi eta, like so. All right. So again, when we're again in this thin grating region, the reason it's thin is for a couple of reasons. Generally, the period that we have is large, so it's large compared to what? Well, it's large compared to, say, the wavelength. So when you get, maybe above the periods like 5 wavelengths or more, that's the kind of our definition that we might use for being a thin grating. When we make that smaller, again, we start to see much higher diffraction angles and fewer diffraction orders coming out of the diffraction grating. So another aspect of these different regimes is whether or not we see other diffraction orders too. So this is going to give us, say, possibility for many diffraction orders, as you found in that one homework problem when you were working that out. All right, so if we want now to know what u is in the observation plane, again, so we have this constant that I sort of mentioned before, which is just all those other terms out in front, times the Fourier transform of u of chi and eta, right? So again, so this is the far field. Diffraction pattern is what we want. So basically now what we want to do is take the Fourier transform of this transmittance function, all right? So let's go ahead and do that. So the Fourier transform of this function, there's actually 2 parts, right? And so what we're going to have then, using our Fourier definitions and tools that we have, is we have a product here, And so we can say that, so it's actually in the chi direction we have a product. Here we just have one function. So we're going to take the Fourier transform of this whole thing, and so we have a product, so we're going to end up with convolution in the Fourier domain, right? So we have the first term. All right, so we'll just break it apart into that and that. All right, so the Fourier transform of the first term, which is this plus m over 2 cosine of 2 pi f0 chi. This is equal to a half, and we have from this 1/2 term out here, delta function of centered at the origin fx, fy in the transform plane. And then here we have m over 2. We factor out a 1/2, say, out of that, or we end up with this m over 4 delta times fx, and this is a cosine, right? So we have two delta functions. One displaced by fx plus f0 fy, and the second here is m over 4 delta of fx minus f0 fy. All right, so this other factor of 1/2 actually comes out of the fact that this is a cosine, and we have that delta functions over 2 in that. Okay, so that's where that other factor of 2 comes from there. Okay, and then our second term, of course, that we have is we have this Fourier transform of excuse me, the rect function of chi over 2w and rect of eta over 2w, and that we know is from our previous example just the area, the sinc of 2wf x from that scaling law that we have, and this area here is 2w times 2w, okay, and so this is also, we need a sinc of 2wfy, okay. So this is the is going to give us an envelope function for that transform that we're going to end up with. And so again, we have the product of these functions here, and very conveniently we have a lot of delta functions, and so the delta functions are nice because they just displace or relocate this envelope function to the centers of those delta functions, or where those delta functions are located. So the combined function from these two functions is the following. So we have now the Fourier transform of u of chi and eta is just equal to a over 2 sinc of 2wf sub y. So that's going to come out because there's no delta functions with y in them. All right, so we don't have to worry too much about that. That's just going to give us a function outside. And then we have a sinc of 2wfx plus m over 2 sinc of 2wfx plus fo. And then we have plus m over 2 sinc of 2wfx minus fo. And fo, of course, is 1 over the period, right? That's what we found from before. Okay, so that's pretty slick. I mean, we just basically relocate the one sinc function at the origin. The other two sinc functions are now displaced, and that's it. Okay, so that's our far field pattern. So this is, we have to multiply it, of course, by, those other terms, that C that I mentioned here. But this is essentially the far field pattern. Okay. Now, there's, so that's the field. So what we would really like, though, is, what we're going to be looking at is the intensity. So in order to do that, of course, we're going to take, the u of xy times its complex conjugate, and that's going to be the intensity. But it's a little messy, right? I mean, how do we get that? If we look at that, we know that these sinc functions are, we have some stuff out there. We have these tails sort of oscillating out there. And so we need to kind of make the problem simpler, so we can get an idea of what's going on. So we'll look at this and we'll say, all right, so we have, without making too much of a wild assumption here, the period that we have, or this frequency corresponding to the period, this is going to be much, much greater than the frequency, say, corresponding to the width of that aperture, all right? So this essentially is saying that, the period is much, much less than the width, all right? So that means that, the separation of these sinc functions are going to be pretty large compared to these, to the widths of the rect function or the sinc functions that are going to be located at those diffraction orders, all right? Okay, so basically with that assumption, all right, so this is our assumption that we'll make, we can now approximate this intensity pattern that we have, I of xy, more simply, and simply, again, say that we have, this is now going to be equal to the area over 2 lambda z squared. Again, this lambda z came from that multiplier that we had outside the integral. Then we have the sinc squared of 2wy over lambda z. Again, that was the non-modulated direction. And then we have sinc squared of 2wx over lambda z. Okay, so that's our, you can think of that as our zero order, right? Our zero order through the center. And then we have the two modulated terms. We have m squared over 4 sinc squared of 2w over lambda z times x plus f0 lambda z. So I'm kind of going back and forth between frequency and spatial values to kind of make it a little more easier to plot or to look at. And then we also have plus this term here, which is m squared over 4 sinc squared of 2w over lambda z, the same modifier, but x minus f0 lambda z. Okay. Okay, so that is the far field intensity pattern. From this thin absorption grating, okay, a thin sinusoidal absorption grating. So right off, you can notice that we have 3 terms. Okay, we have a zero order and a plus and minus order. That comes about because we had started with a cosine function here for the amplitude transmittance function. So no big surprise there. But there's some other things that we can draw to here. So let's look at this and think about some things that we discussed earlier in the class. So let's say we have our, here's our grating, right? So here's our square grating, like so. And it's propagating, let's plot this out here, all right? So here's z, of course, and here's our x and y direction. All right, so so again, this term here is going to give us a sinc squared function along the axis like that, and then we have these other two terms. Okay, so we're going to have one of those is going to go in this direction out here. All right, but what is that direction actually? So what is this angle that we have for that relative to the axis? Well, remember we illuminated this with a normally incident plane wave. All right, and here we have lambda over z. All right, or I'm sorry, lambda over the period for that grading. And this, so this should kind of remind us of something that we looked at before. Remember, we have the grading equation, right? So we have sine theta 1 minus sine theta 2 is equal to lambda over the period. So lo and behold, we have that. And if this were 0 degrees, we have that. So this angle that we have is kind of buried in here. This is lambda over the period. All right, so we actually have, and this is like also equal to the tangent of theta for small angles that we have. And so basically, this formula here is kind of encompassing the grading equation in it. All right, it just kind of folds it into it from the basic nature of the diffraction process. And so this tangent theta, we can write that as also being equal to lambda z over the period divided by z. So this is z, and so if we multiply, z by top and bottom, basically is what we're doing here. We have this displacement out here now is just equal to lambda z over the period. We take that. That's our x distance divided by z, and that gives us the tangent of that angle or the sine of that angle if it's a small angle. Okay, so the plot that we have, again, is going to look like something like this. So we have a nice sinc squared function centered at the origin. We can normalize that to a value of, say, 1 out there. The width of that is, again, determined by that scaling function that we have. And so the overall width of that is just going to be equal to twice this value. And so this is equal to lambda z over w. This is x is what we're plotting there. And then if we go out here a distance of lambda z over the period, or f0 lambda z, we're going to have another sinc squared function, but this one's only going to come up to a value which is equal to m squared over 4. However, it has the same width as this. I didn't maybe draw it the same, but the width of that, it's the same, right? It has the same scaling factor there, all right? So it also has a width of lambda z over w, and then we also have another one out here at minus f0 lambda z, same kind of nature as this other one. All right, so again, that also has a lambda z over w with a maximum height of m squared over 4, okay? All right, so let's look at one final thing. So we have a sinusoidal modulation. We end up with a cosine function, and we have 3 orders, a plus and minus 1 order. So here's our plus 1, here's our minus 1, and we have a 0 order out there. So what is the diffraction efficiency of this grading? All right. Well, the maximum so what is that diffraction efficiency? Well, it's going to be equal to the intensity of this term, right? So the intensity of that term plus the intensity of that term plus the intensity of that term, all right? So we have the 0 order term. This we have is just equal to 1/4, right? This is, we have a value of 1/4 for that center value. So this is for the 0 order. For the plus and minus 1 orders, we end up with this 1/4 from this term out here. We have, 1/4 from that if we scale that, and that's multiplied by everything. And then we have the plus and minus 1 orders, that same factor of 1/4 out front, but times m squared over 4 for those two values. And so this is equal to m squared over 16, okay? So the maximum diffraction efficiency for the absorption grating is not that great. It's equal to 1/4 plus 1/16 plus 1/16, right, for those two, which is equal to 0.375. All right. The rest of that, the other 62.5%, is absorbed, right? It's an absorption grating. So this is not a very high efficiency, and also the maximum efficiency you can get in a diffraction order, which is usually the sort of the field component of interest, is just 1/16 or 0.0625. 6.25%. All right, so it's not very high for a useful part of that diffracted field. Okay, so that is the thin absorption grating. All right. Again, analyzed very nicely using this this method of Fourier analysis that we have. All right, so we didn't get very high efficiency there. So let's I mentioned too that we can also modify the phase when we were talking about different types of gratings. Let's see, is that 6? Yeah. So yeah. So let's look at a sinusoidal phase grating, or a thin sinusoidal phase grating now. Can at least get started on that. All right, so here again, so we're going to, what we're looking at here now is we have this is kind of like the types of holograms you're doing in the lab. So you have this medium, and then there's some modulation here of either, this is, say, the thickness here that we have is D. So we might be, say, modulating the refractive index. And this direction, again, is our chi direction. So we have n of chi is modulated, or it is modulated in some way. And so with that, so we might have a n0 plus a delta n, actually, of chi as a index modulation of that grating, and when we multiply it, so we have 2 pi n over lambda times d. This is going to give us some phase modulation in that grating. So these are functions of chi, like so. All right. So what is our so this phase, just for completeness here, so we have our phase, and here is chi. So now, instead of modulating the amplitude, we're going to modulate that phase about some bias level out here. And once again, we're going to have a kind of a peak to valley modulation depth of m. All right. So with this, we can write the amplitude transmittance function for this thin sinusoidal phase grating as T sub A of chi and eta is now equal to this phase modulation exponential of j m over 2, sort of this half height above the bias level, times the sinusoidal modulation of the phase sine of 2 pi chi over the period. So we have that. So again, the period is just equal to our normal period that we have. And again, we limit the size of this, okay? So we're going to limit the size of that to, say, 2w. And so once again, we'll have a rect function of chi over 2w. And in the eta direction, the same thing, rect of eta over 2w. So we have those amplitudes surrounding or limiting the extent of that grading. Okay, so again, following our same procedure, we illuminate this with again, our normally incident plane wave illumination. That converts the T sub A to a field directly past here. And then that's going to continue propagating, and we're going to look for the far field pattern. All right, so that's just equal to our T sub A of chi and eta at this point. Okay, and so we're going to want to take the Fourier transform of that. So, this part, of course, is easy. What about this part, though? This looks a little more interesting. You know how to take the Fourier transform of that phase function, sinusoidal phase function? Neither did I. Okay, so Goodman, he's a smart guy. He figured this out. Yeah, so what you do is you look at it in terms of a power series, okay? Well, it's already an exponential, all right? So you have an exponential of an exponential, right? Sine can be expressed as an exponential. So let me bear with me for a moment. So let's just look in the math tables and see what we can find. You know, a lot of people spent their lives, you know, doing this stuff before they had televisions and smartphones, you know. So fortunately for us. And so there is a nice mathematical expression for this, exponential of j m over 2 sine of 2 pi f0 chi, all right? So this has a series expansion in terms of Bessel functions. So it does have the exponentials, like you were saying, but they're weighted exponentials, and so we have here an infinite series of Bessel functions. Q equals minus infinity to infinity of the Bessel function of order Q with a argument of this amplitude of that modulation. So we have m over 2 exponential j 2 pi q, this order term again, here for this series, f0 chi. So that's really slick, you know, because again, just like before, you know, when we were trying to do the simplify that Fourier integral, so you know, where we use the binomial expansion. Here's another expansion, except now we have Bessel functions. We have these weighted exponentials in the Bessel functions. Now, yeah, go ahead. Question.
Is that the first Bessel function or the qth Bessel function?
This is the order, all right? So this is like the 0, first, second, there's, yeah.
It's just a matter of, I couldn't tell from your handwriting whether it was 1 or q.
Oh, I see. It's a lack of readability issue. Okay, sorry. Yeah, so that order changes, all right? And there's an infinite series of these. So what we're going to see is, unlike, even though this is a sinusoidal grading, modulated grading, unlike the absorption grading, where we ended up just with 3 orders, now you see we're going to have, this looks like we're going to end up with an infinite series, an infinite number of orders, okay, where that light is going. Okay, so I think we're at the end of the period now, or a little bit over. So I'll stop here. We'll pick this up next time, and we'll see that we can get more efficiency as well, but it's still not where we'd like. And so that's, again, a motivation for going to a more of a volume grading for our analysis, or for our useful holographic elements. Okay, so we'll see you next time. Yeah.
Same as M.
This is the M, and that's the M there.
And then in the grading, the sinusoidal grading picture, you labeled the thickness as D.
The
Plot
width.
on the right is his phase factor.
Oh, okay.
So it's like his phase amplitude double.
Okay.
Your left picture, you labeled that box as width.
Oh, the left picture? Oh, what did you want me to label? Oh, this is a D.
I was just wondering if it was the same as M.
Oh, this is N. This is an N.
Well, no, if it's the same. I know it now. I was wondering if it was the same as the M in the phase plot.
Well, these are related, okay? M and this phase here is kind of, the modulation. The modulation is going to come from this, in this example, from the index modulation.
I was just wondering if it was the same as the
No, it's not exactly the same. Yeah, I was just using it as an example of where to get that from. So, okay, so we'll see you on Thursday.